Hello everyone, can you hear me? I had I did a new mic setting. I'm using another software so my voice would be a little different, but I hope it is clear to everyone. And yeah, last time I said I would be doing a physics stream, but the thing is I wanted to do that stream in a second channel, but like in order to allow live streaming, I have to verify my phone number and I already used the same phone number twice in two other channels, and I can't use it the third time. So I have to wait a little while before. They said I have to wait at least 1 year, and like after a few days, that 1 year period will be complete. So I have to wait for a few days till I can start live streaming in my science channel. Anyways, until then, I'll be reading about operating systems. Okay, new section, concurrency. They have a lot of code bits, but the thing is, I'm streaming on Windows, so I don't know if the code bit would work. So I'm using this online C compiler and hope everything works well here. Okay, part 2, concurrency. A dialogue on concurrency. I like 2 pages. Or never mind, one single page for this one is fine. And thus we reach the second of our 3 pillars of operating systems, concurrency. I thought there were 4. Nope, that was an older version of the book. Okay, so what is concurrency, oh wonderful professor? Well, imagine we have a peach. Peaches again. What is it with you and peaches? Ever read T.S. Eliot, the love song of J. Alfred Prufrock? Do I dare to eat a peach? All that fun stuff? Oh yes, in English class in high school. Great stuff. I really like the part where interrupting. This has nothing to do with that. I just like peaches. Anyhow, imagine there are a lot of peaches on a table and a lot of people who wish to eat them. Let's say we did this way. Let's say we did it this way. Each eater first identifies a peach visually and then tries to grab it and eat it. What is wrong with this approach? Hmm. Seems like you might see a peach that somebody else also sees. If they get there first, when you reach out, no peach for you. Exactly. What should we do about it? We'll probably develop a better way of going through this. Maybe form a line, and when you get to the front, grab a peach and get on with it. But what's wrong with your approach? Sheesh, you have to do all the work? Yes. Okay, let me think. Well, we used to have many people grabbing for peaches all at once, which is faster. But in my way, we just go one at a time, which is correct, but quite a bit slower. Best kind of approach would be fast and correct, probably. You're really starting to impress. In fact, just told us everything we need to know about concurrency. Well done. I did. I thought we were just talking about peaches. Remember, this is usually the part where you make it about computers again. Indeed, my apologies. One must never forget the concrete. Well, as it turns out, there are certain types of programs that we call multi-threaded applications. Each thread is kind of an independent agent running around in this program, doing things on the program's behalf. But these threads access memory, and for them, each part of memory is kind of like one of those peaches. If we don't coordinate access to memory between threads, the program won't work as expected. Makes sense? Kind of, but why do we talk about this in an OS class? Isn't that just application programming? Good question. A few reasons actually. First, OS must support multi-threaded applications with primitives such as locks and condition variables, which we'll talk about soon. Second, the OS itself was the first concurrent program. It must access its own memory very carefully, or many strange and terrible things will happen. I see. Sounds interesting. There are more detail, I imagine. Indeed, there are. Concurrency and a thread. Let's open the code GitHub. Thus far, we have seen the development of basic abstractions the OS performs. We have seen how to take a single physical CPU, turn it into multiple virtual CPUs, thus enabling the illusion of multiple programs running at the same time. We have also seen how to create illusion of a large private virtual memory for each process. This abstraction of the address space enables each program to behave as if it has its own memory, when indeed the OS is secretly multiplexing address spaces across physical memory. In this chapter, we introduce new abstraction for a single running process, that of a thread. Instead of a classic view of a single point of execution within a program, a single PC where instructions are being fetched and executed, a multi-threaded program has more than one point of execution, multiple PCs, each of which being fetched and executed from. Perhaps another way to think of this is that each thread is very much like a separate process, except for one difference. They share the same address space and thus can access the same data. The state of a single thread is thus very similar to that of a process. It has a program counter, PC, that tracks where the program is fetching instructions from. Each thread has its own private set of registers it uses for computation. Thus, if there are two threads that are running on a single processor, when switching from running one to running the other, a context switch must take place. The context switch between threads is quite similar to context switch between processes, as the register states of T1 must be saved and the register state of T2 restored before running T2. With processes, we saved state to a process control block. Now we will need one or more thread control blocks to store the state of each thread of a process. There is one major difference though. In the context switch we perform between threads as compared to processes, the address space remains the same. One major difference between threads and processes concerns the stack. In a simple model of the address space of a classical process, which we will now call a single threaded process, there is a single stack usually residing at the bottom of the address space. So program code, heap, and then stack. However, in a multi-threaded process, each thread runs independently and of course may call various routines to do whatever work it is doing. Instead of a single stack in the address space, there will be one per thread. Stack 1, stack 2. Let's say we have a multi-threaded process that has two threads in it. The resulting address space looks different. In this figure, you can see two stacks spread throughout the address space. Thus, any stack allocated variables, parameters, return values, and other things that we put on the stack will be placed in what is sometimes called thread local storage. The stack of the relevant thread. You might also notice how this ruins our beautiful address space layout. Before, the stack and heap could grow independently, and trouble only arose when you ran out of room in the address space. Here, we no longer have such a nice situation. Fortunately, this is usually okay, as stacks do not generally have to be very large. Before getting into the details of threads and some of the problems you might have in writing multi-threaded programs, let's first answer a more simple question. Why should you use threads at all? As it turns out, there are at least two major reasons you should use threads. The first is simple: parallelism. Imagine you are writing a program that performs operation on very large arrays, for example, adding two large arrays together, or incrementing the value of each element in the array by some amount. If you are running on a single process, the task is straightforward. Just perform each operation and be done. However, if you are executing the program or a system with multiple processes, you have potential of speeding up this process considerably by using the processors to each perform a portion of the work. The task of transforming your standard single threaded program into a program that does this sort of work on multiple CPUs is called parallelization. And using a thread per CPU to do this work is natural and typical way to make programs run faster on modern hardware. The second reason is a bit more subtle to avoid blocking program process due to slow I/O. Imagine that you are writing a program that performs different types of I/O, either waiting to send or receive a message or for an explicit disk I/O to complete or even implicitly for a page fault to finish. Instead of waiting, your program may wish to do something else, including utilizing the CPU to perform computation or even issuing further I/O requests. Using threads is a natural way to avoid getting stuck. While one thread in your program waits, the CPU scheduler can switch to the other thread which are ready to run and do something useful. Threading enables overlap of I/O with other activities within a single program, such as much like multi-programming did for processes among across programs. As a result, many modern server-based applications make use of threads in their implementations. Of course, in either of the cases mentioned above, you could use multiple processes instead of threads. However, threads share an address space and thus make it easy to share data. Hence, a natural choice when constructing these types of programs. Processes are much more sound choice for logically separating tasks when little sharing of data structures in memory is needed. An example, thread creation. Let's get into some of the details. Say we wanted to run a program that creates two threads, each of which does some independent work. In this case, printing A or B. The code is shown in figure 26.2. So we have my thread, printf. Okay, so I put common.h over here. And we need common underscore threads.h. Uh, it's in the include. Common underscore threads. Underscore threads dot h. Let's do t0.c. Let's do a main actually. Simple thread creation. It's in threads intro. So main begin, BA, and then main end. Hold on. Now let's go over here. After creating two threads, let's call them T1 and T2. So what does this go to? So if argc is not 1, so usage main, then exit. Now p thread p1 p2, so main begin. So p thread, so creating a thread. Uh, this is where the thread will be stored in this p1 variable. I don't know what null is, maybe probably the argument. And then my thread is a function it will run, and actually a is the argument. I don't know what null is. Maybe the return type. And then we have print f. So convert this into a character. Why is this mentioned as a void? So join waits for the threads to finish. Um, okay, and main end. After creating the two threads, let's call them T1 and T2. The main thread calls p thread underscore join. Well, I mean, it's with a capital P. But I don't know why it's done like this. How do I scroll that side? So all this assert p create. So why do this? Which waits for a particular thread to complete. It does so twice, thus ensuring T1 and T2, we should have called it P1 and P2, will run and complete before finally allowing the main thread to run again. When it does, it will print main end and exit. So join pauses the main thread until P1 finishes. Overall, 3 threads were employed during this run. The main thread, T1 and T2. Let's examine the possible execution ordering of this little program. In the execution diagram, 26.3, page 5, this is 26.3. So starts running, print main begin, create thread 1, create thread 2, wait for T1. That's the join over here. Then runs, prints A, returns, and then go back to main, waits for T2, runs, prints B, and returns. But isn't it like, aren't these happening at the same time because they're threads? Like this over here, it looks like a single threaded thing. Let's examine the possible execution ordering of this little program. Oh no, wait. So this part will only run after. Okay, so it creates thread 1, then this runs. Creates thread 2, then this runs. But is it possible for main to create thread 2 while thread 1 is running? I think that is possible. That's the entire point, right? Let's examine the possible execution ordering of this little program. In the execution diagram, time increases in the downward direction, and each column shows when a different thread, the main one or thread 1 or thread 2 is running. Note, however, this ordering is not the only possible ordering. In fact, given a sequence of instructions, there are quite a few depending on which thread and scheduler decides to run at a given point. For example, once a thread is created, it may return immediately, which would lead to execution shown in 26.4. This is another possible trace. So starts running, prints main begin, creates thread 1, and then immediately starts running. Then creates thread 2, and then this runs. So wait for thread 1, returns immediately, T1 is done, and then waits for T2, and then print end. We could also even we also could even see B printed before A. If say the scheduler decided to run thread 2 first, even though thread 1 was created earlier, there is no reason to assume that a thread that is created first will run first. Figure 26.5 shows us final execution ordering, with thread 2 getting to strut its stuff before thread 1. So starts running, print main begin, creates thread 1. Scheduler decides not to run it now and then creates thread 2. Thread 2 runs, waits for T1. Thread 1, hold on, wait. Uh, waits for T1. So when it encounters this, so thread 1 has to finish after this has encountered. And then waits for T2, returns immediately, T2 is done, prints. And what I was thinking is that when it hits this line, thread 1 is supposed to be already completed. But it's the other way. As you might be able to see, one way to think about thread creation is that it is a bit like making a function call. However, instead of first executing the function and then returning to the caller, the system instead creates a new thread of execution for the routine that is being called. And it runs independently of the caller, perhaps before returning from create, but perhaps much later. What runs next is determined by the OS scheduler. Although the scheduler likely implements some sensible algorithm, it is hard to know what will run at any given moment in time. As you might also as you might also as you also might be able to tell from this example, threads makes life complicated. It is already hard to tell what will run when. Computers are hard enough to understand without concurrency. Unfortunately, with concurrency, it simply gets worse, much worse. But the thing is, if this is the issue, like if you want the thread to do something, you can just use join to wait for it to complete, right? And then you can be sure that that execution is done. The simple thread example we showed above was useful in showing how threads are created and how they can run in different orders depending on how the scheduler decides to run them. What it doesn't show you, though, is how threads interact when they access shared data. Let us imagine a simple example where two threads wish to update a global shared value. The code we'll study is in figure 26.6, page 7. This is d1.c. So I will just get d1.c, copy, and then paste that on main. What is this? The simple thread example we showed above was useful in showing how threads are created and how they can run in different orders depending on how the scheduler decides to run them. What it doesn't show you, though, is how threads interact when they access shared data. Let us examine a simple example where two threads wish to update a global shared value. Here are a few notes about the code. First, as Stevens suggests, we wrap the thread creation and join routines to simply exit on failure. So my thread, you have a for loop and returns null. So what do they mean failure? We wrap the thread creation and join routines to simply exit on failure. They have this common underscore thread, speed thread create, assert that this is equal to 0, which means this function was successfully created. Same with join. Okay, I understand what this is doing. For a program as simple as this one, we want to at least notice an error occurred. If it did, why not do anything very smart about it? Thus, capital P thread underscore create simply calls P thread underscore create and makes sure the return code is 0. If it isn't, P thread create just prints a message and exits. Okay. Second, instead of using two separate function bodies for the worker threads, we just use a single piece of code and pass the thread as an argument, in this case a string. So we can have each thread print a different letter before its messages. So thread, my thread, the letter, yeah, the letter goes here. So printf begin address of it. Let me run this. Cast from pointer to integer of different size. Let me just remove this for now. Cast from pointer to integer of different size. It's not working here. Let me just skip this. How do I put in the arguments? Wait, what's the usage of this? Finally, and most importantly, we can now look at what each worker is trying to do. Add a number to the shared variable counter and do so 10 million times in a row. Thus, the desired final result is 20 million. Okay, so begin counter 0. A begin, A done. B begin, B done. And then main done, counter 20, should 20. Oh, and now the counter is a wrong number. Unfortunately, when we run this code, even on a single processor, we don't necessarily get the desired result. Sometimes we get this. Let's try it one more time just to see if you have gone crazy. After all, aren't computers supposed to produce deterministic results as you have been taught? Perhaps your professors have been lying to you. Not again, it's wrong. Not only is each run wrong, but also use a different result. A big question remains, why does this happen? I think we did a similar exercise with processes, where each processing is where each process is updating the same variable, but it doesn't work. Wait, processes don't have like shared address space, right? I have to reread that section again. But I do remember doing something similar. You should always learn new tools that help you write, debug, and understand computer systems. Here we use a neat tool called disassembler. When you run a disassembler on an executable, it shows you what assembly instructions make up the program. For example, if we wish to understand how low-level code, to, how and if we wish to understand the low-level code to update a counter, we do object dump to see the assembly code. Object dump dmain brings up produces a long listing of all instructions in the program, neatly labeled, particularly if you compile with the G flag, which includes symbol information in the program. The object dump program is just one of many tools you should learn how to use. A typical like GTP memory profilers like Valgrind or Purify, and of course the compiler itself are others that you should spend time to learn more about. The better you are using your tools, the better systems you'll be able to build. The heart of the problem, uncontrolled scheduling. To understand why this happens, we must understand the code sequence that the compiler generates for the update to counter. In this case, we wish to simply add the number 1 to counter, thus the code sequence for doing so might look something like this in x86. So move this to EX, add 1 to EX, and move EX back to this memory. This example assumes that the variable counter is located at address this In this three instruction sequence, the x86 move instruction is used to first get the memory value at the address and put it into register EAX. Then the add is performed, adding 1 to the contents of the EAX register. Finally, the contents of the EAX are stored back into memory at the same address. Let us imagine one of two threads. Let us imagine one of our two threads enters this region of code and is thus about to increment counter by 1. It loads the value of counter, let's say it's 50 to begin with, into register EX and thus EX 50 for thread 1. Then it adds 1 to the register, thus EX 51. Now something unfortunate happens. The timer interrupt goes off, thus the OS saves the state of currently running thread to the thread's TCB. Now something worse happens. Thread 2 is chosen to run and it enters the same piece of code. It also executes the first instruction, getting the value of counter and putting it into EX. Remember, each thread when running has its own private registers. The registers are virtualized by the context switch that saves and restores them. The value of counter is 50 at this point and thus thread 2 has EX50. Let's then assume thread 2 executes the next two instructions, increment EX by 1 and then saving the contents of EX to counter. Thus the global variable of counter now has value 51. Finally, another context switch occurs and thread 1 resumes running. Recall that it has just executed move and add and is now about to perform the find and move instruction. Recall also that EX51, thus the find and move instruction executes and save the value to memory. The counter is set to 51 again. But simply what happened is code increment counter that the code to increment counter has been run twice. And counter which started at is 50 is now only equal to 51. A correct version of this program would have resulted in variable counter equal to 52. Let's look at a detailed execution trace to understand the problem better. Assume for this example, the above code is loaded at address 100 in memory, like the following sequence. Note for those of you who uh, used to nice RISC like instruction sets, x86 has a variable length instructions. This move instruction takes up 5 bytes of memory and only 3. So OS, thread 1, thread 2, PCAX counter. So we have this move and add, and then 51 is saved in EX. Interrupt save T1 restore T2. So when it restores T2, we have 100, 0 and 50. Move, add, move. Now we have 51 here. 51 here. Now interrupt save T2 restore T1. Now 51 is stored back at EX and counter is saved to 51 again. With these assumptions, what happens is shown in figure 26.7. Assume the counter starts at value 50 and trace through this example to make sure you understand what is going on. What we have demonstrated here is called a race condition, or more specifically, a data race. The results depending on the timing of the code's execution. With some bad luck, context switches that occur at untimely points in the execution, you get the wrong result. In fact, we may get a different result each time. Thus, instead of deterministic computation, we call this result indeterminate, where it is not known what the output will be and it is indeed likely to be different across runs. Because multiple threads executing this code can result in a race condition, we call this code a critical section. A critical section is a piece of code that accesses a shared variable. or more generally, a shared resource, and must not be concurrently executed by more than one thread. Or what if they're only reading the thing? If they're reading a constant value, then that shouldn't be a problem, right? What we really want for this code is what we call mutual exclusion. This property guarantees that if one thread is executing within the critical section, the others will be prevented from doing so. Virtually all of these terms, by the way, were coined by Edgar Discast. I forgot how he pronounces his name. Who was a pioneer in the field and indeed won a Turing Award because of this and other work. See his 1968 paper on cooperating sequential processes for an amazingly clear description of the problem. We will be hearing more about him in this section of the book. I forgot how you pronounce his name. Atomic operations are one of the most powerful underlying techniques in building computer systems. From the computer architect to concurrent code, what we are studying here to file systems, database management systems, and even distributed systems. The idea behind making a series of actions atomic is simply expressed with the phrase all or nothing. It should either appear as if all of the actions you wish to group together occurred or that none of them occurred, with no in between state visible. Sometimes the grouping of many actions into a single atomic action is called a transaction. An idea developed in great detail in the world of databases and transaction processing. In our theme of exploring concurrency, we'll be using synchronization primitives to turn short sequences of instructions into atomic blocks of execution. But the idea of atomicity is much bigger than that, as we will see. For example, file systems use techniques such as journaling or copying on write in order to atomically transition on disk state, critical for operating correctly in the face of system failures. If that doesn't make sense, don't worry, it will in some future chapters. One way to solve this problem would be to have more powerful instructions that in a single step did exactly whatever we need done and thus remove the possibility of untimely interrupt. For example, if we had a simple instruction that looked like this, assume this instruction adds a value to memory location and the hardware guarantees that it executes atomically. When the instruction executed, it will perform the update as desired. It could not be interrupted mid instruction because that is precisely the guarantee we receive from the hardware when an interrupt occurs. Either the instruction has not run at all or it has to run to completion. There is no in between state. Hardware can be beautiful thing, no? So atomicity is a bunch of instructions executing together or not at all, right? Yeah, yeah. In this context, means as a unit, which sometimes we take as all or nothing. What we like to do, what we would like to execute, what we would like is to execute the three instruction sequence atomically. As we said, if we had a single instruction to do this, you could just issue that instruction and be done. But in the general case, we won't have such an instruction. Imagine we were building a concurrent B tree and wish to update it. Would we really want the hardware to support an atomic update of B tree instruction? Probably not, at least in the same instruction set. Thus, what we will instead do is the hardware for a few useful instructions upon which we build a general set of what we call synchronization primitives. By using this hardware support in combination with some help from the operating system, we will be able to build a multi-threaded code that accesses critical sections in a synchronized and controlled manner, and thus reliably produces the correct code despite the challenging nature of the concurrent execution. Pretty awesome, right? This is the problem we will study in this section of the book. It is a wonderful and hard problem and should make your mind hurt. If it doesn't, then you don't understand. Keep working until your head hurts. You then know you're headed in the right direction. So, how to support synchronization? What support do we need from the hardware in order to build useful synchronization primitives? What support do we need from the OS? How can we build these primitives correctly and efficiently? One more problem waiting for another. This chapter has set up problem for concurrency as if only one type of interaction occurs between threads, and that of accessing shared variables and the need to support atomicity for critical sections. As it turns out, there is another common interaction that arises. One thread must wait for another to complete some action before it continues. This interaction arises, for example, when a process performs a disk IO and is put to sleep. When the IO completes, the process needs to be reused from its slumber so it can continue. It's not reused, it's roused. Thus, in the coming chapters, we will not only study how to build support for synchronization primitives to support atomicity, but also for mechanisms to support this type of sleeping waking interaction that is common in multi-threaded programs. If this doesn't make sense right now, that is okay. It will soon enough. When you read the chapter on condition variables, uh, when you read the chapter on condition variables, if it doesn't by then, well, it is less okay, and you should read that chapter again and again until it does make sense. Aside key concurrency terms. Therefore, terms these four terms are so central to concurrent code that we thought it worthwhile to call them out explicitly. A critical section is a piece of code that accesses a shared resource, usually a variable or a data structure. A race condition arises when multiple threads of execution enter the critical section roughly at the same time. Both attempt to update the shared data structure, leading to a surprising outcome. An indeterminate program consists of one or more race conditions. The output of program varies from run to run, depending on which thread ran when. The outcome is thus not deterministic, something we usually expect from computer systems. To avoid these problems, threads usually use some kind of mutual exclusion primitives. Doing so guarantees that only single thread ever enters a critical section, thus avoiding races and resulting in deterministic program outputs. Before wrapping up, one question that you might have is, why are you studying this in OS class? History is the one word answer. The OS was the first concurrent program, and many techniques were created for use within the OS. Later, with multi-threaded processes, application programmers also had to consider such things. For example, imagine the case where there are two processes running. Assume they both call write to write to a file, and both wish to append the data to the file. To do so, both must allocate a new block, record node of the inode of the file where this block lives, and change the size of the file to reflect the new larger size. Because an interrupt may occur at any time, the code that updates the shared structures are critical sections. Thus, OS designers from the very beginning of the introduction of the interrupt had to worry about how the OS updates internal structures. An untimely interrupt causes all of the problems described above. Not surprisingly, page tables, process lists, file system structures, and virtually every kernel data structure has to be carefully assessed. with the proper synchronization primitives to work correctly. Yeah, I will lead this section and then I will end the stream. So, interlude thread API. This chapter briefly covers the main portion of the thread API. Each part will be explained further in subsequent chapters as we show how to use the API. More details can be found in various books and online sources. We should note that the subsequent chapters introduce the concept of logs and condition variables more slowly. With many examples, this chapter is thus better used as a reference. So, thread creation, the first thing you have to be able to do is write uh, the first thing you have to be able to do to write a multi-threaded program is to create new threads, and thus some kind of thread creation interface must exist. In POSIX, it is easy. So pthread.h, we have pthread create, the pthread pointer, attribute, uh, function name, and argument. This declaration might look a little complex, particularly if you haven't used function pointers on C, but actually it's not that bad. There are four arguments: thread, attribute, start routine, and argument. The first thread is appointed to a structure of type pthread underscore t. We will use this structure to interact with this thread, and thus we need to pass it to pthread underscore create in order to initialize it. The second argument, attribute, is used to specify any attributes this thread might have. Some example might include setting the stack size or perhaps information about scheduling priority of the thread. An attribute is initialized with a separate call to pthread initiate. Pthread attribute initiate. See the manual page for details. However, in most cases, the defaults will be fine. In this case, we simply pass the value null in. Third argument is the most complex, but is really just asking which function should this thread start running in. In C, we call this a function pointer, and this one tells us the following is expected: a function name, so start routine, which is passed single argument of type void, which returns a value of type void pointer. If this routine instead required an integer argument instead of a void pointer, the declaration will look something like this. Okay, so void start routine int and int arg. If instead the routine took a void pointer as an argument but returned an integer, it will look something like this. So a function that returns int but takes in void. Finally, the fourth argument, arg, is exactly the argument to be passed to the function where the thread begins execution. You might ask, why do we need these void pointers? Well, the answer is quite simple. Having a void pointer as an argument to the function or start routine allows us to pass in any type of argument. Having it as a return value allows the thread to return any type of result. Let's look at an example in figure 27.1. Here we just create a thread that is passed two arguments packaged into a single type we define ourselves. Uh, Once you create a thread, you really have another uh, live executing entity, complete with its own call stack running within the same address space as all the currently executing threads in the program. Thus, the fun begins. So figure 27.1. So creating a thread create. Since when is there assert? So structure int A, int B. Uh, let's start with the main. Yeah, P thread P. Arguments 10 and 20. RC. Oh, we are checking if the return value was is 0 to make sure the creation was successful. So pointer to P. Okay. So this over here, the variable which stores P thread goes here. No attributes. My thread, oh yeah, this function goes here. And then args goes over here. And the args is a structure. Args is this structure over here. A structure with 10 and 20. So convert arg to my argt and then print if A and B. And now in the main thread, wait for the P to complete and then print. Done. What is this void over here though? If I remove this, what happens? Nothing. The example above shows how to create a thread. However, what happens if you want to wait for the thread to complete? You need to do something special in order to wait for completion. In particular, you must call the routine pthread underscore join. The routine takes two arguments. The first is of type pthread t and is used to specify which thread to wait for. This variable is initialized by the thread creation routine. If you keep it around, you can use it to wait for that thread to terminate. And what's the second argument? Second argument is a pointer to the return value you expect to get back. Because the routine can return anything, it is defined to return a pointer to void. Because pthread join changes pthread join routine changes the value of the passed in argument, you need to pass in a pointer to that value, not just the value itself. Okay, so this over here takes a pointer to our return value. If I do 5 int and int return value is equal to 0, rv is percentage t return value. If I run, it should work fine. No, it's not fine. Returning int from a function with return type int pointer. Okay, what if I do this? It has to be a pointer, right? But if I return a stack variable, it's going to get deleted after this then. Otherwise, I will have to use global variables to access this then. Is there like a help? I want to see this second variable being used to properly understand it. Once thread, let's see, thread is finished running, the main thread which has been waiting inside a pthread join routine then returns and we access the return value. The value is returned from the thread, namely whatever is in my return t. Okay. A few things to note about this example. First, oftentimes we don't have to do all the painful packing and unpacking of arguments. For example, if we just create a thread with no arguments, we can pass null in as an argument when the thread is created. Similarly, we can pass null into pthread join if we don't care about the return value. We know that we use wrapper functions here. Specifically, we call malloc, pthread join, and pthread create, which just call their similarly named lowercase versions and make sure the routines did not return anything unexpected. Second, if we are just passing in a single value, we don't have to package it up as an argument. Figure 27.3 shows an example in this case. Life is a bit simpler as we don't have to package arguments and return values inside of structures. So in figure 27.2, single thread is created again and passed a couple of arguments via my arg structure. My arg, my return value. So why is this capital M? Is this the thing they're using? Okay, let's see. Let's just copy. So my args, uh, first the p thread, my return value, r values. Where is the r value? Okay, this is initialized. My arg underscore t args 10 and 20. So p thread create. This is the variable, no attributes. This is the function, and this is the argument. So this structure over here, goes to arg, but it's converted to my arg underscore t. and then print f arg a arg b, so 10 and 20, and then my return r values malloc. So we are creating stuff in the heap. Okay, new heap value goes to r values, and then assert that r values is not equal to null, and do x and y, set x and y, and then return or convert it to void pointer. Okay. Hold on, I don't understand. When we set r values x to 1 and r values y to 2, r values, we create a malloc. So threads don't have a separate heap, right? So it's this over here, malloc to r values return, and the threads r value is duplicated to here. It's a reference copied, like pointer copy to here, to r values on the main thread. Wait, so r value within this thread function gets deleted, right? This is in the heap, this is in the stack, and it's pointing to the place in the heap. So this stack value is deleted, and the memory in the heap is assigned to this stack value instead, the r values of the main thread, right? And then we free r values. So whatever this is pointing to, which was created over here, is now freed in the heap. We got 27.3. Let's look at that. So my thread main, my thread void 100. They're directly passing a number now instead of a variable name. And then long int r value. So they're passing in 100, which is converted to long int, long decimal value. It's printed over here. Then we do a value plus 1. Its value plus 1 is set over here. But I don't understand. Doesn't value get deleted? Because this is a stack function, and after this function ends, value, the temporary return object gets deleted, right? Or does it like assign to r value first and then it deletes? We get 27.3 showed us an example. In this case, life is a bit simpler, as we don't have to package arguments or return values inside of structures. Third, we should note that one has to be extremely careful with how values are returned from a thread, Specifically, never return a pointer which references to something allocated on the thread's call stack. If you do, what do you think would happen? Think about it. Here's an example of a dangerous piece of code modified from example figure 27.2. So allocated on the stack before it was, yeah, before it was malloc. Now it's allocated on the stack. Wait, what about arg though? What about this value here? Is this not in the stack? In this case, the variable oops is allocated on the stack of my thread. However, when it returns, the value is automatically deallocated. That's why the stack is so easy to use after all. Thus, passing back a pointer to a now deallocated variable will lead to all sorts of bad results. Certainly, when you print out the values you think you returned, you will probably be surprised. Try it and find out yourself. Fortunately, the compiler GCC will likely complain when you write code like this. Finally, you might notice that the use of a pthread create a thread followed by an immediate call to pthread join is a pretty strange way to create a thread. In fact, there's an easier way to accomplish this exact task. It's called a procedural call. Clearly, we will usually be creating more than just one thread, waiting for it to complete. Otherwise, there is not much purpose to using threads at all. We should note that not all code that is multi-threaded uses the join routine. For example, a multi-threaded web server might create a number of worker threads and then use main thread to accept requests and pass them to the workers indefinitely. Such long-lived programs thus may not need to join. However, a parallel program that creates threads to execute a particular task in parallel will likely use join to make sure all such work completes before exiting or moving on to the next stage of computation. Yeah, I still don't understand this bit. Wait, I have an idea. Print f, print, print, print the pointer to this. Print the pointer to arc. Arc is a pointer, right? Format T accepts, but your argument has long. Wait. Well, how do you print a pointer again? Is it X? Maybe B. Wait, I get this and I get this. By doing decimal, okay, I just wanted to check whether it's like how it's copied. Yeah, but anyways, this is on the stack. So why is it like, why doesn't this get deleted then? Beyond thread creation and join, probably the next most useful set of functions provided by the POSIX threads library are those for providing mutual exclusion for a critical section via logs. The most basic pair of routines to use for this purpose is provided by the following: mutex lock and mutex unlock. The routine should be easy to understand and use when you have a region of code that is a critical section and thus needs to be protected to ensure correct operation. Locks are quite useful. You can probably imagine what the code looks like. The intent of the code is as follows: if no other thread holds the lock, when pthread mutex lock is called, the thread will acquire the lock and enter the critical section. If another thread does indeed hold the lock, the thread trying to grab the lock will not return from the call until it has acquired the lock, implying that the thread holding the lock has released it via the unlock call. Of course, many threads may be stuck waiting inside the lock acquisition function at a given time. Only the thread with the lock acquired, however, should call unlock. Unfortunately, this code is broken in two important ways. The first problem is the lack of proper initialization. All locks must be properly initialized in order to guarantee that they have correct values to begin with, and thus work as desired when lock and unlock are called. With POSIX threads, there are two ways to initialize lock. One way to do this is to use pthread mutex initializer as follows. So lock pthread mutex initializer then sets the lock to default values and thus makes the lock usable. The dynamic way to do it at runtime is to make a call to pthread mutex initialize as follows: rc initialize lock now. First argument to this routine is the address of the lock itself, whereas the second is an optional set of attributes. Read more about the attributes yourself. Passing null in simply uses the default. Either way works, but we usually use the dynamic latter method. Note that a corresponding call to pthread mutex destroy should be made when you are done with the lock. See the manual page for all the details. The second problem with the code above is started phase to check error codes when calling lock and unlock. Just like virtually all library routines you call in a Unix system, these routines can also fail. If your code doesn't properly check error code, the failure will happen silently, which in this case would allow multiple threads into a critical section. Many use wrappers which assert that the routine succeeded, as shown in figure 27.4. More sophisticated non-type programs which can't simply exit when something goes wrong should check for failure and do something appropriate when the call does not succeed. They said 27.4. So pthread mutex lock. It checks whether it was successful. The lock and unlock routines are not the only routines within the pthread library to interact with logs. Two other routines of interest. So pthread mutex try lock, pthread mutex time lock. These two calls are used in lock acquisition. The try lock version returns failure if the lock is already held. The timed lock version of acquiring a lock returns a timeout or after acquiring the lock, whichever happens first. Thus, the time lock with a timeout of 0 degenerates to the try lock case. Both of these versions should generally be avoided. However, there are a few cases where avoiding getting stuck in a lock acquisition routine can be useful, as we will see in future chapters. The other major component of any threads library, and certainly in the case with POSIX threads, is the presence of a condition variable. Condition variables are useful when some kind of signaling must take place between threads. If one thread waiting for another to do something before it can continue, uh, yeah, two primary routines are used by programs wishing to interact this way. So condition wait and condition signal. To use a condition variable, one has to, in addition, have a lock that is associated with this condition. When calling either of the above routines, this lock should be held. First routine, pthread condition wait, puts the calling thread to sleep and thus waits for some other thread to signal it. Usually, when something in the program has changed that the now sleeping thread might care about. A typical usage looks like this. Pthread mutex lock, pthread mutex initializer, condition, some condition. So lock it first, while radius 0, and wait for some condition, and then unlock it. In this code, after initialization of the relevant lock and condition, a thread checks wait, a thread checks to see if a variable ready has yet been set to something other than 0. If not, the thread simply calls the wait routine in order to sleep until some other thread wakes it. The code to wake a thread which would run in some other thread looks like this. Lock ready 1 p thread code signal condition mutex unlocked. A few things to note about this code sequence. First, when signaling as well as modifying the global variable ready, we always make sure to have the lock held. This ensures that we don't accidentally introduce a race condition into our code. Second, you might notice that the wait call takes a lock as a second parameter, whereas the signal call only takes a condition. The reason for this difference is that the wait call, in addition to putting the calling thread to sleep, releases the lock when putting said caller to sleep. Imagine if it did not. How could the other thread acquire the lock and signal it to wake up? However, before returning after being woken, the p thread condition wait reacquires the lock and thus ensuring that any time the waiting thread is running between the lock acquired at the beginning of the wait sequence and the lock release at the end, it holds the lock. Yeah, I need to get a better understanding of this. One last oddity, the waiting thread rechecks the condition in a while loop. Instead of a simple if statement, we will discuss this issue in detail when we study condition variables in a future chapter. But in general, using a while loop is simple and safe thing to do. Although it rechecks the condition, there are some pre-thread implementations that could spuriously wake up a waiting thread. In such a case, without rechecking, the waiting thread will continue thinking that the condition has changed even though it has not. It is safer thus to view waking up as a hint that something might have changed rather than an absolute fact. Note that sometimes it is tempting to use a simple flag to signal between threads instead of a condition variable and associated log. For example, we could rewrite the waiting code above to look uh, more like this in the waiting code. The associating signal code will look like this. So radius 1. Don't ever do this for the following reasons. First, it performs poorly in many cases. Spinning for a long time just wastes CPU cycles. Second, it is error prone. As recent research shows, it is surprisingly easy to make mistakes when using flags as to synchronize between threads. In that study, roughly half of the uses of these ad hoc synchronization were buggy. Don't be lazy, use condition variables even when you think you can get away with doing so, without doing so. If condition variables sound confusing, don't worry too much yet. You'll cover them in great detail in subsequent chapters. Until then, it should suffice you to know that they exist and to have some idea how and why they're used. All of the code examples in this chapter are relatively easy to set up. Okay. Introduce the basics of pthread library. All right. Aside thread API guidelines, there are a number of small but important things to remember when you use a POSIX thread library, or really any thread library to build a multi-threaded program. They are: keep it simple. Above all else, any code to lock or signal between threads should be as simple as possible. Minimize thread interactions. Try to keep the number of ways in which thread interacts to a minimum. Each interaction should be carefully thought of and constructed with tried and true approaches. Initialize locks and condition variables. Failure to do so will lead to code that sometimes works and sometimes fails in a very strange way. Check your return codes. Be careful with how you pass arguments to and return values from threads. Each thread has its own stack. Always use condition variables to signal between threads and use the manual pages. Okay, just one more thing. I'm about to reread this again and then I will end the stream. So, a critical section is a piece of code that accesses a shared resource. A race condition arises if multiple threads of execution enter the critical section at roughly the same time. Both attempt to update the shared data structure, leading to a surprising outcome. An indeterminate program consists of one or more race conditions. The output of a program varies from run to run. To avoid these problems, threads should use some kind of mutual exclusion primitives. Doing so guarantees that only a single thread ever executes and a single thread ever enters a critical section, thus avoiding races. Okay, I will end the stream here then, and yeah, I'll continue studying these chapters. I think I will finish the entire concurrency chapter before streaming anything else, or I might stream in the language learning channel maybe. Uh, yeah. Anyways, see you guys next time. Bye.